All right, so I'm starting the recording for today's lesson. If you have any questions or comments and you don't feel comfortable being recorded, please just chat them to me and I'll get them at the end of the lesson and I can answer them then, because now I won't be able to because of the get me out of here. I won't be able to because of I can't see it while I'm in this system. Sorry, I was doing two things at once here.
Bring your fork.
Yeah. Thank you.
Where's this at? Why is this not showing up? Should be recording this. I'll stop this recording. Get me out of here. There it is. All right, so here's today's recording. Little pause there in the beginning. But we're dealing with harmonic motion. And so harmonic motion is a back and forth motion that repeats itself over and over again. So a couple terms that we're going to need to use: the term oscillation. Oscillation is a movement back and forth between 2 points. Every wave comes from a disturbance. Disturbances cause waves, and waves carry energy. So down here you can see just a bunch, like a guitar string. This is a up and down wave, what we call a transverse wave. Sound waves longitudinal. Water wave is a surface wave. Visible light's an electromagnetic wave. So these are all different types of waves. Electrons' orbits are in waves. All those different waves carry energy. Essentially what happens is you apply a force. So this hand would pull out, right, on the, whatever this was, the tongue depressor. And then this force here, F, this is a restoring force. So this depressor itself wants to get back to its equilibrium position. So it applies the force. And then when it gets to equilibrium, now it has inertia that keeps it moving forward. That's the inertia there. So it still has a forward velocity. So it goes past the point. Then the restoring force comes back in. Then it goes to equilibrium, and so on and so forth. And this is what causes an oscillation. It has to do with inertia and restoring forces. We learned this formula earlier when we talked about Hooke's law. So F equals negative kx. This is our formula for finding the amount of restoring force. So I have them all written down here at the end of the slide. F is the restoring force. X is the displacement from equilibrium. So remember, that was equilibrium, right? And if we're doing the tongue depressor, this would be X. That's your displacement from equilibrium. If we're talking about something else that's not, if we were talking about a spring or something, it's the distance from equilibrium. That's your starting point. K is the force constant, or how stiff the object is, how hard it is to get it to go to expand or extend. When we talked about springs, right, we called it the spring constant, how stiff, or the elasticity. And when we talked about elasticity, we said it was how elastic it was. It's the same idea. And the negative just tells you that it's a restoring force, that the force applied is opposite the force that you pulled away with. So the force is always going to be bringing it back to equilibrium. Again, this is from Hooke's law. We already went over this formula when we went over springs. Work equals 1/2 kx squared. That's the work done in restoring the spring or the oscillating object. Periodic motion. We're dealing with periodic motion in this And this is something that repeats itself over and over again. So things like clocks, pendulums, springs, anything that repeats itself over and over again, that's considered periodic motion. Oh, I wrote right on top the definitions here. So a period is the time to complete one oscillation. That's your period. So when you're doing your lab, if you have a pendulum, the pendulum gets pulled up to here, it swings down and back. That's one period. It's the whole way to get back to where it started. So a period is getting back to where you started. So like a sine wave, that's one period. The time it takes to go from here to the same point. And frequency is the number of oscillations per unit time. The units for frequency are hertz, whereas period, it's second. So whenever you see hertz, like megahertz or kilohertz or any kind of hertz, that's frequency. And that's how often it happens, right? If you're counting how many times per unit time. And the relationship between frequency and period, F equals 1 over T. They're inversely related. One goes up, the other one goes down. Like there's always a question, if you go to the moon and you run your pendulum back and forth on the Earth, and then you go do the same thing on the moon, which one has a longer period? Which one takes more time?
The
Earth or
moon, because it has less gravity.
Good. The moon takes more time. It has a longer period. So bigger period means smaller frequency because there's less gravity on the moon. Very good. All right, so let's try this. It says a 0.75 kilogram toy oscillating on a spring completes a cycle over 0.6 seconds. What's the frequency of the oscillation? So we have the mass. The time is 0.60 seconds. And we want to find the frequency. So this time is actually the period. So we don't have to do anything super fancy. F equals 1 over T, 1 over 0.6, whatever that is. .67 hertz. So this is cycles per second, right? That's how we get that hertz. Hertz are cycles per seconds. Anybody have any questions there? Pretty straightforward. All right, so if we're dealing with the period and the frequency of a simple harmonic oscillator, so this would be like something going up and down or back and forth where we have a mass and the constant. This is the formula that we use. So this would be like an object going back and forth, which we're going to look at here in a minute, or up and down. To find the period and the frequency, we would use this formula, the relationship between the mass and the constant. Simple harmonic motion, which sometimes we characterize or shortened to SHM, simple harmonic motion. This is the name given to oscillatory motion that we usually talk about. Most of the things that we're doing are simple harmonic motion, which means they have the same amplitude every time. And under ideal conditions, they would never stop going back and forth. They would go back and forth forever. They wouldn't slow down. So that is simple harmonic motion. Just wondering if you're wondering. This formula is important. This is the formula for a pendulum, simple pendulum. And you'll need this in your lab when you need to find the period of the pendulum. You'll use this formula. So L, this L here, this is the length of the string. And it goes from top to bottom, right to the bottom of the bob. So you can see the length goes the whole way down to you can use the middle or the bottom. It doesn't matter. And then G, this is actually the absolute value of G. So when you're doing the lab, make sure that you don't put you're not getting an imaginary number here. You're not putting a negative into this square root. So make sure that this is the magnitude of G. And make sure this L is in meters. So make sure you make a note of that for when you do the lab. This is just showing pictures of the equilibrium situation where we have a positive amplitude and a negative amplitude. So positive amplitude and equilibrium here is in the middle. That's your middle position, your zero, like if the ball was just left to hang at rest. And then we pick the ball up, we give it a positive amplitude. And then as it drops, it goes through its equilibrium down to its bottom amplitude. And remember, at these points, U equals 0, right? U at the top and U at the bottom. I'm sorry, not U, K. Remember, your kinetic energy at the top equals 0 and your kinetic energy at the bottom equals 0. And U is the max, or I should say max equals the max at the top and the bottom. And then in the middle, U equals 0 and K is the max. So you have your biggest velocity in the middle of your peak. And that's what this is showing over here. If you were to drop a line straight down here, you can see that when it's in its equilibrium position, it has its maximum velocity. When it has maximum amplitude, has 0 velocity. So just interesting. We talked about that already this year. This is a little bit of review. And here it is horizontally. We just looked at it vertically, but the same idea, maximum amplitude. And we already looked at this slide earlier this year where we have maximum amplitude gives you 0 velocity. And then when it's at equilibrium, we have maximum velocity. Same thing with work. And this gives us our formula, which I'm just going to put up here and explain to you. So this is the law of conservation of energy. This is the total energy. So the total energy equals the kinetic energy plus the potential energy, remember? So then all we're going to do is isolate to solve for V at any point. So this is your velocity at any point. So let's just look at the object on the spring. Right, if I pull it out here to amplitude A, that's this A. Then if it's at X, right, X is here, you can see X squared minus A squared. So you have less velocity or more velocity here than here. If X equals A, your velocity is 0, or if X equals A. If x equals 0, that's here, then your velocity is a max. So this is the square root. It'd probably be better to write a. And his pencil is really fat today. Probably better to write this as plus or minus a square root of k over m, just so you don't put that a in the square root sign. But you can see when this is 0, when that goes to 0, now we have this equation here. V max equals that. And then just to take that square root sign out and put it over here, it's just shorthanded for V max. So really you have two equations here. You have this equation here and this equation here. You're just seeing this is the velocity at any point. This is your maximum velocity, which is at one point. This is at equilibrium.
What does the A stand? Was that again?
Amplitude.
Okay.
And your amplitude is defined. I don't know if I had that definition in there. Your amplitude, I can write, is your max displacement from equilibrium. That's the definition of amplitude. Your maximum displacement from equilibrium.
Is that so? That's at equilibrium, or
At equilibrium, your amplitude is 0.
okay.
So at equilibrium, amplitude is 0, V is the max. Those are the two things you need to know. All right.
Bless you.
Thanks. Let's try a problem. It says a mass spring system in simple harmonic motion in the horizontal direction. So that means we got a little system like this with a little spring here. And we got an object on the spring. We're going back and forth. We assume it's frictionless down here. If the mass is 0.25 kilograms and the spring constant is 12 newtons per meter, and the amplitude, kind of got away from me here. My poor picture got too tight. Excuse me. And the amplitude is 15 centimeters. Well, that's 0.15 meters. We all know that. What would be the maximum speed of the mass? So if it's frictionless, does the actual mass of this thing matter? No, is the answer. Remember our formula, we just learned it. V max equals, it does matter. I don't even know where my brain, I was too busy sneezing to think. K over M times A. That's the maximum velocity. Of course it matters. I mean, if it's heavier, the spring's not going to be able to push it as easy. So K is 12 divided by 0.25 times 0.15. So 12.25 divide square root 0.15 times 1.04 meters per second. That's part A. Where does this occur? Does anybody know? Does anybody remember what I just said?
Is it at half amplitude?
No?
0.
At 0 what?
Oh,
What's the name for the 0 position?
Oh, equilibrium.
equilibrium.
It's at equilibrium. So this is at equilibrium. And then part C says, what would be the speed at the half amplitude? So half amplitude, what's X going to equal at our half amplitude position? So if this is the amplitude, the half amplitude is here, right? That's X. So that means this object now is in the middle somewhere. It's going back towards there. So is it going to be a greater speed or less speed than 1.04?
Less.
Less, because at this point it's 1.04. Out here it's 0. So it's got to be between 0 and 1.04. So half amplitude is half of 15. That's 7.5 centimeters or 0.075 meters. So C equals V equals K over M times A squared minus X squared. V equals the square root of 12 times 0.25 times 0.15 squared minus 0.075 squared. Zero 0.90. Anybody else get that? Does anybody have any
Oh, yeah.
questions on what I did there? Anybody need anything clarified there?
So it's the amplitude squared minus the X, which is
Yep, the
displacement,
displacement.
and then that's okay. I see what's going on, I think.
Anybody else have any questions here?
Wait,
All right.
I don't
What?
see why the 0.15 is not inside the square root of the first one, but is in the second one.
Well, because this is A squared, so you could write it as K over M A squared, right? But the square root of A squared is A, so that just comes out to be K over M times A. Does that make sense?
Yeah. Wouldn't that make the entire value of the second one half? And then,
No, because it's squared. And if you have V equals the square root of K over M A squared minus X squared. Oops.
Monday moment.
Right, like that? What do you mean a half? It's not A minus X squared. Those are different things.
no, okay, I see. It's the square root of 3/4, not a half, ultimately.
Correct. Anybody else? Anybody? All right. Try this one on your own.
I got an answer.
Uh-oh.
I almost freaked out.
Why?
You wrote 0.05. I was like, whoa, whoa, whoa.
I got 0.22.
Yeah.
That's what I got.
Yay. Pretty exciting. Here you go. Another one. Oh my goodness. Who invited the dog?
Well, that was me. Sorry, I left my mic on.
That's all right. I'm not that upset.
So, I got the answer.
Okay.
You want me to?
Let's give it a
say
try. So we got the mass. We got K. We have A. These are like nothing compared to the last chapters, huh?
Oh yeah, this is way better.
Way better. This is probably the easiest section we got going here. $1.4 meters per second.
Can you make the next exam all these questions?
Good
Wouldn't that be
one.
nice?
Oh, quick question. When you have the 49 Newton meter spring constant, do we have to take into consideration that the spring, when it's going up past its equilibrium point, like the gravity could be stronger than the constant?
You're saying, do we have to draw a free body diagram on it if we were looking for the forces acting on it?
Well, like, I'm wondering if the amount of force changes. Because it's interfering.
It's definitely not a constant force. No, it does change. It's a variable force.
But we can still generalize it with this formula.
Yeah.
Okay.
I think one last thing, just this idea of resonance and natural frequency. And this is just a little conceptual stuff. Natural frequency is the frequency you vibrate at naturally when you're struck. And then resonance is being able to match the natural frequency. So there's this, if you can do that with this ball, there used to be something called a click clack. You ever know what a click clack is? It had like two balls like this, and then you would click them together, and then they would go above your hand and click together and then come back down. If you hit the right rhythm, you could get them to go up and down over and over again.
Oh yeah,
Oh,
I got a
that's
couple of
nice.
those from the dentist's office.
Yeah, those are click. Well, I called them click clacks. I don't know. I think that's their formal name. But either way, that's the idea of resonance. If you can time your hand moving up and down, you can get them to go at a natural frequency that matches the resonant frequency, or a resonant frequency that matches their natural frequency. And that's how you get the big amplitudes. So this is just some terminology that you should be familiar with: resonance and natural frequency. And here's our quiz. Class is just about over. Give us a shot.
Does swing imply like go back and forth?
30 swings, yeah. 30 cycles. 1,
Okay.
2, 3.
So wait, is this like the end of class quiz?
Yep.
Oh, okay.
my physics teacher in high school had a really bad joke about frequency. You guys want to hear it?
Yeah.
Go right ahead.
Go,
I don't
go.
know if it's a joke, but it's just a way to remember like what the frequency is. But he said, "Oh, the ocean." There's this time when I was standing in the ocean and I kept getting hit by waves one after another, and he was like, "Ow, the freaking sea hurts." Is that funny? Do you like that?
That's really good.
It's mildly humorous.
Good.
I wonder if that's his own joke or if he found that somewhere.
I'm not going to give him credit, but I will say that he said it. So
Quite often did he say it? Or just
he
once?
said it at least 2 or 3 times over the course of the day.
All right, does everybody have this down? Can I get out of the screen?
Yeah.